So to kind of round out our conversation about beams and bending, we're going to talk about something that is super, super common in the real world that we haven't really encountered yet. It's kind of a special case, and that is composite beams. And a composite beam just means it's a beam that's made up of more than one thing. It's a composite of multiple things. So, for example, you might see like a wood beam. The center is wood, and maybe it's surrounded by steel plates on either side to give it some additional support. Or the most common one, the one we see all the time in engineering, especially if you're in civil engineering, is reinforced concrete, right? So concrete, when we pour it, typically if we were to pour a slab of concrete, we like to have rebar in there. Steel beams, steel rods that go throughout that concrete slab to give it additional support. Since concrete is really good in compression and steel we know is really good in tension, they work together to kind of offset each other's weaknesses, and you get this really, really great composite material that we love to use for roads and floors and ceilings and walls and all sorts of things. Anytime we use concrete, we're often using this reinforced concrete. So this is something that we see a lot in the real world, and something that we deal with kind of as a special case in strength of materials. So really the important thing to note with these composite beams is that what we're going to do in order to deal with the fact that we have two different materials, two different moduli of elasticity that we're working with, we need to do a transformation. We are going to transform these two separate things and pretend like they're the same material. Make a transformation. So what I mean by that is, let's say I have, I've got one material on top here. It has one modulus of elasticity, and then I have a different material that is bonded to it on the bottom here that has some different modulus of elasticity. And they each have, they each have a thickness, and they each have some original width. So this is our original width here. What we're going to do is transform this using our transformation factor, what we're going to call a transformation factor N. N is just a ratio of those moduli of elasticity. It's the ratio that relates those two materials together. We call this the transformation factor. And basically what that does is allows us to say, okay, let's pretend like instead of having this blue on bottom, let's pretend like they're both orange and they both have the same modulus of elasticity. So that transformation factor is going to change the geometry so that we can have a modulus of elasticity that matches. So what it'll do is it'll keep that top geometry the same, right? We had that E1, it still has a thickness of B, or a thickness of T1, and that base width of B. But now if we're transforming the bottom using this transformation factor, just a ratio of the moduli of elasticity, I'm going to say, okay, now instead of having this value E2, we're going to pretend like this is made of E1, retains its same thickness though, but now we get a new base width. This new base width, so this new base width is going to be our transformation factor times the original base width. Right, so this N times B. So it's this relationship of these moduli of elasticity to change this so that the geometry looks a little bit different, right? We have a new base width here, but we can treat this all as one material now. So this would just be an oddly shaped beam that we need to do special things with our moment of inertia or find a new centroid for in order to find things like our bending moment, find our stress, and then we can transform it back into our original shape to see what we're actually working with in terms of bending moment or whatever attributes we might be interested in finding for this beam. So let's take a look at one quick little example of how we might use this. So this example asks us to first transform this wood steel beam we have on the left side here into just a steel beam. And then if a moment of 2 kilonewton meters is applied, what is the bending stress at points B, up there in the upper right corner, and point C on the steel in the lower left? And they give us their moduli of elasticity for the wood and the steel, 12 gigapascals for wood, 200 gigapascals for the steel. And then we have our geometry over here of our wood is 150 by 150 millimeters, attached by steel on the bottom, 20 millimeters by 150 millimeters. So we've got kind of two parts we're looking at here. One is to transform it to a steel beam, and then we're going to find bending stresses using our bending stress equation that we've been talking about. Moment times y over moment of inertia. So first thing we need to do is transform this into just a steel beam. So they tell us which one we're looking at, right? Just steel. So what we're going to do is use our transformation factor n. N is going to be our modulus of elasticity of the wood over the modulus of elasticity of the steel. So in this case, that's 12 over the 200. Punch that into my calculator, I get 0.06. 0.06 is the transformation factor. And I'm going to use this in order to transform the wood portion. So what I want is I want to get a new base width. My height is going to stay the same. It's still going to be that 150, but that base is going to be different. And my new base is the transformation factor times the original base. So 0.06 times that original base of 150 millimeters. And when I punch that into my calculator, I'm getting 9 millimeters. So what that means, what that looks like, is if I were to redraw this in its transformed version, I would still have that original steel portion, the 20 millimeters thickness at the bottom, 150 base for the steel portion, but now that wood portion that was on top becomes a steel portion that is 9 millimeters thick. Right, so instead of this nice like two little squares situation, two rectangles, I have a very skinny rectangle on our top here. Still has that same thickness of 150, but my steel at the bottom remains unchanged. So my wood became steel, right? If we transform it into steel, this is like the equivalent steel type. So this is actually what we're going to use to calculate our bending stress. Now that everything is in one modulus of elasticity, I'm going to look at my bending stress equation here, get all the info that I need for this shape that all has one modulus of elasticity. So they gave us our moment. They said the moment is 2 kilonewton meters, or 2,000 newton meters. I like to convert all my units up front. 2,000 newton meters. And let's see what else. I need my distance y from the centroid out to that point, right? So each of these points are in different locations. Our C is in that lower left corner on the steel, but notice B actually isn't here anymore. B used to be right about here. right? But because of that transformation, B has been pushed in, and we're going to call this B prime for now. So we're going to calculate this B prime, and we're going to have to make a transformation to get back to where B actually is. So B prime is what we'll call this one. But because I transformed this thing, it has a new centroid, right? This steel shape has its own separate centroid from the original shape. Let's go ahead and calculate a centroid real quick. Our centroid equation is the sum of the centroid of all parts times area over the sum of all the areas. So I've got two kind of obvious rectangles here. So that's going to be my bottom rectangle. The area is 0.15. Oops, 0.15 times 0.02. Again, I'm just converting everything into meters as I go so that everything can have consistent units. For this, you don't have to. We could just leave it as the 150 and the 20, and it would just work out that our centroid would be in millimeters. It's up to you. You can put it in millimeters or meters. It doesn't really matter for this. But our centroid of this bottom shape here would happen 10 millimeters up from the bottom. So that would be 0.01. And then our area, put it down here at the bottom too, 0.15 times 0.02. And then our area for the transformed wood section that's now steel is 0.009 times that 0.15. Right, that 0.15 stays the same, but now we have that 9 millimeter thickness. So that goes in this equation too, 0.009. Whoops, I'm going to just stack these times 0.15 times, I need my centroid location of this other shape. So the centroid happens halfway through the rectangle, so that would be 75 millimeters, but I need to add on this 20 that's below it, right? That 20 pushes it up by 20, so 20 plus 75 is 0.095. It's a little messy, but I can punch all of that into my calculator to get my centroid, which is 0.0364 meters. Or if you did it in millimeters, you can have 36.4 millimeters. Either way is fine. So now I can get my Y locations for the distance from the centroid here. Centroid somewhere in there, 36.4 millimeters. Distance from my centroid to point C and from my centroid to point B prime. And then the only other thing I'm missing in my bending equation here is the moment of inertia. So I'm gonna erase all my transformation factor stuff. I got what I needed. I might write that 0.06 down though. But the transformation factor N was 0.06. Keep that in case we need it later. The last thing we need is our moment of inertia. So we're going to have to use our parallel axis theorem for this because we've transformed this into two rectangles that don't share a centroid, right? So we need to do our summation of Ix, it's AD squared. And normally I'll do a table for this, but you can also just do it right in the equation. Since these are two rectangles, their Ix portion is 1/12 base times height cubed. 1/12 base times height cubed. and then A times distance from the centroid squared. So distance between the centroid of the shapes versus the overall centroid squared. So I can put this all into one big equation. My bottom rectangle, 1/12, 150, which again I'm going to convert into meters. 0.15 times height, 0.02 cubed, plus the area, 0.15 times 0.02. And then d squared here, again, that distance is the distance from the centroid to the centroid of my shape. So in this case, 0.036 minus 0.01, right? 0.01 is the centroid of this rectangle. And that distance gets squared. And then I just add on that same thing, but for my other shape, the transformed wood shape. So that's going to be, my base is 9 millimeters now, 0.009 times the height of 0.15 cubed, plus that area, 0.009 times 0.15, right? Again, just base times width. And now again, it's the distance from the centroid from the centroid of the shape to the centroid of the overall shape. So we said our centroid of our shape was 0.095. Then the centroid of the total shape minus 0.36 squared. And again, it doesn't matter which order you subtract these in, because it's going to get squared, your positive is going to go away, right? Or your negative is going to go away. It's going to come out as a positive either way. So I take this whole long thing, plug all of that into my calculator to get a moment of inertia of 9.385 times 10 to the negative 6th meters to the 4th. Ooh, so all that work just so I can find the bending stress in points B and C. So let's do that. We've got all the ingredients. Move all of this. And my centroid stuff I don't need anymore. I'm just going to take those values, put them up here so I can reference them. Perfect. So I've got my bending stress. Let's do our bending stress for point C first. Right, that one's a little simpler. We don't have to go through any transformations or anything. It's just going to be our moment, 2,000 Newton meters, times C, so that's our distance from the centroid to where the point is located. So that's going to be 0.0364 meters over my moment of inertia, 9.358 times 10 to the negative 6th meters to the 4th. That gives me a bending stress at point C of 7.78 megapascals. And that's it. That's all we have to do for that point C. It didn't get transformed. It was always made of steel, so we're just going to end it there for our bending stress at point C. For our bending stress at point B, we're going to do the same thing, but there's one extra step that we have to do. So at B, really what we're finding is that bending stress at B prime. B prime, the transformed steel bending stress. So again, it's that 2,000 Newton meters times the distance. The distance from B prime to the centroid is Let's see, that overall distance is 0.17, and then we can subtract out the centroid. And we'll just put that into our calculator. Over that moment of inertia. And so what I get here for the bending stress for B prime is 1.71 megapascals. But again, that is if this were made of steel, but it is not actually made of steel. So what we want to do is we want to use our transformation factor. This is not the right number. I wrote down the wrong number, sorry. All right, this is 28.6. I was like, wow, that number seems really low. That was not the right number. Okay, when you punch this into the calculator, sorry, this is 28.6 megapascals. What we have to do is we have to apply our transformation factor again to get it from the bending stress of the steel into the bending stress of the wood. So that relationship is really just this transformation factor, where our bending stress at B is the transformation factor times the bending stress at B prime. So that's our 0.06 times 28.6, and that is where I got the 1.71 megapascals from. I just read a little bit too far ahead when I pulled out my calculated values. So this would be our actual bending stress at B in the wood, right? So it's a matter of just transforming things, treating it all as one thing, and then remembering to transform it back. And that's how we treat these composite beams to solve problems whenever we want to have more than just a single material.